So thank you. I'm audible. So thank you, organizers, Professor Athanase, Professor Subhojoy, and other organizers for inviting me and also giving this opportunity to say something about Finsler geometry here. As you know, in most of the talks, you heard about this Finsler geometry, Finsler metric, and maybe in coming talks also, you'll see several Finsler metric. So I'll introduce a little bit, and also finally I'll say something about what we are doing in Finsler geometry. So in the renowned lecture of 1854, the title was On the Hypotheses Which Lie at the Foundation of Geometry. Riemann discussed the possibility of a metric more general than square root of a quadratic differential form. In particular, a metric which is fourth root of a quadratic differential form. The origin of Finsler geometry seems to appear in this habilitation lecture. Formally introduced by Finsler in 1918 in his thesis under supervision of Carathéodory and developed by several geometers including Taylor, Burward, Cartan, Buchmann, Roon, Hashiguchi, several persons, and towards end of the previous century, Chern also took interest in the development of especially global Finsler geometry. Several results he extended. In the first statement of classic survey of Finsler geometry, Buchmann wrote that the term Finsler space evoked in most mathematicians the picture of an impenetrable forest whose entire vegetation consists of tensors. Then he went on to prove that the exclusive use of tensor was a historic accident and suggested a more geometric way of the study of Finsler geometry. In fact, his view was to see in every tangent space a convex body which was parameterized in the manifold. Rather than looking on the this tensor notations, his view is to just, as you also saw in the lecture of Ohshika, that in every tangent space you are looking on a convex body. We'll see a bit more about all these things. Since the last decade of previous century, Chern and others have extended several known results like Gauss-Bonnet, sphere theorem, etc. for Riemannian geometry to the Finsler geometry. So Chern actually, his view was this Finsler geometry he saw as a generalization of Riemannian geometry. We'll see that how Riemannian geometry as a particular case of Finsler geometry. And recently, several people working in Teichmüller theory, convex geometry, metric geometry, they have paid attention towards the Finsler geometry as various metrics on Teichmüller spaces like Teichmüller metric, Thurston metric, earthquake metric, etc. They are Finsler, they are non-Riemannian. Now, to measure the arc length of a piecewise curve, as you know, for any curve, even in Euclidean geometry, so suppose you have this alpha as a curve from say AB to any manifold, and you want to measure its length of this alpha, is you have to integrate the speed of this curve. So basically, you need actually norm on each tangent space along the curve. Now, a reasonable tool to compute the arc length of a curve on a smooth manifold is a Riemannian metric on the manifold, which is smoothly varying family of inner products on the manifold. One can ask or think, can we talk about a family of norms rather than inner product on the manifold? And the answer is yes. We'll see such a norm, and such a norm we'll call as a Minkowski norm, will define precisely. And the Finsler structure on a smooth manifold is a family of Minkowski norm, one on each tangent space of the manifold. Now first define Minkowski norm on a vector space. So let V be n-dimensional real vector space. A continuous function is called a Minkowski norm if it satisfies the following three conditions. greater than equal to 0 and f psi is equal to 0 if psi equal to 0. It is called non-negativity condition. F is positively homogeneous of degree 1. So this is important because generally in functional analysis norm, we are we take this condition that f of k xi is equal to mod of k f of xi, but here we consider only f k xi is equal to k f xi with only positive k. So it means that f of minus xi may not be equal to f of xi. So I mean it's not symmetric norm. And the third is usual this triangle inequality. So this is my Minkowski norm. Now in Finsler geometry, it's well known word this indicatrix. So the unit sphere centered at origin is called indicatrix of the Minkowski norm. Now here is a fact that the indicatrix of a Minkowski norm is convex hypersurface. Convex hypersurface means the interior of a convex bounded subset of P vector space, consisting of origin in its interior. And interestingly, if a convex hypersurface is given to you which contains the origin, so if a convex hypersurface is given, and suppose here is the origin, it may not be symmetric, then there exists a unique Minkowski norm. So for example, suppose this is your space, and you know this is my unit vector. So you can measure any vector in terms of this unit. So this is, suppose this is your 1, so you can talk about this as k times 1. So you can talk about the norm of any vector in this vector space. So in fact, this indicatrix determine the Minkowski metric, and Minkowski metric, of course, they determine the unit sphere. So I mean, this is the reason why the Bushman viewpoint that you are you think about this. I mean, in every tangent space, a convex body. But from differential geometric point of view, I mean, here convex body mean it may be, it may not be even, I mean, C1 differentiable. So just like some convex body, maybe some polygons. But now from differential geometric point of view, we put some stronger condition. So this Minkowski norm is said to be strongly convex if it is smooth on this non-zero part, and the Hessian of f square at any non-zero point is positive definite. Geometrically, the smoothness of the norm is equivalent to the smoothness of the indicatrix. So this norm is smooth, it's equivalent to saying that our indicatrix is smooth. And the strong convexity is equivalent to saying that the indicatrix has strictly positive Gaussian curvature. So now we'll only consider this a strictly convex Minkowski norm that is smooth. It's in every tangent space we have a smooth indicatrix and it has positive Gaussian curvature. And the consequence of this strong convexity is that f is positive on for any non-zero vector, it's always strictly positive, and it satisfies triangle inequality. So triangle inequality turns out to be is a consequence of this strongly convex condition. Now, for example, you consider this LP norms. So LP norm is a Minkowski norm for any p greater than or equal to 2, but it's strongly convex if and only if p is equal to 2. So for p lies between 1 and 2, this is smoothness condition is violated, and for p greater than 2, this is strong convexity is violated. So only Euclidean norm among all the LP norm is strongly convex Minkowski norm. Now this is, I mean, this is an example of a norm. So let us take this Euclidean norm and you just deform by this quantity. So on R2, this is an example of strongly convex Minkowski norm. An example of what we call Rander's norm, which is just deformation of Euclidean norm. And its unit sphere, unit indicatrix, you can think of look like this ellipse, but center is not at the origin. Now, we'll say something how it differ from Euclidean norm. So, let Rn F be a Minkowski space and delta be a Minkowski metric induced from F, then this is Euclidean if and only if the ball centered at a and radius r is an ellipsoid. So, our Minkowski space is Euclidean if and only if it's actually ellipsoid with center at, the center at the center of the ellipse. And the second interesting proposition for this distinction between this Euclidean metric, delta is a Minkowski metric on Rn, then every isometry of delta is an affine transformation. This portion is actually a consequence of the Major-Ulam theorem. And the group of isometries of delta is conjugate within the affine group of subgroup of isometry of Euclidean space. And this Minkowski space becomes Euclidean if and only if it's conjugate to the full group of isometry of Euclidean space. So, this is an interesting consequence. So, if its group of isometry is the conjugate of full group of isometry of the Euclidean space, it's actually Euclidean. This is another, yes.
What kind of subgroup it can be? Is it like a closed
So suppose, this is your ellipsoid and is a convex set, suppose it contains the origin, and here is your Euclidean origin. So, basically your subgroup is, you just take this translation along the line joining this origin and this origin. So, the orthogonal group composed with this translation along this line is the subgroup actually, right. So, this is the next proposition, is this, yes. No, it depends on so for strongly convex, I think no, yeah. But for if you just take Minkowski norm, so it may be different. Yeah. Yeah. So this is another proposition. So it says that the square of the Minkowski norm is always C infinity away from the origin and is C1 at, is only C1 at origin and has derivative 0 there, and it's C2 if and only if it's Euclidean. So this is the characterization of the Minkowski norm to be Euclidean. Now, let's come to our Finsler metric. So a Finsler metric on the smooth manifold is a continuous function such that f is actually a function from tangent bundle to non-zero part of the tangent bundle to R is a smooth, and its restriction to every tangent space is actually strongly convex Minkowski norm. So for me, this Finsler metric is a function from tangent bundle to R such that its restriction to each tangent space is actually strongly convex Minkowski norm. But you can think of, if you don't like to do differential geometry, you don't like to compute curvature, etc. And for you, it's just in every tangent space, it's just a Minkowski norm. But for me, I will consider this is strongly convex Minkowski norm on each tangent space. This function is called Lagrangian, and of course, as we discuss that in general, this, I think, yeah, this minus should be, yeah. So in general, this fx minus xi is not equal to minus fx xi. The length of minus xi is not equal to f of xi, and is said to be reversible if it's equal. For example, Riemannian metric is an example of a Finsler metric, and that's a reversible Finsler metric. So these are examples. So you can think of this Rn, and in each tangent space you take a Minkowski norm, and such a structure is considered to be flat space in Finsler geometry. Just like your Euclidean setup, in every tangent space you fix a Minkowski norm, same Minkowski norm, just via translation. A Riemannian metric on a manifold defines a Finsler structure given by this. You just take this Riemannian metric, and this is the norm induced from this Riemannian metric is our Finsler structure. Now, this is an interesting class of Randers metric. So, if on a manifold, if G be a Riemannian metric and take this theta is a norm which is everywhere is less than 1, right. So, this theta, you take any vector, theta of V is less than 1 for every B in the tangent space. So, if such conditions satisfy, this is a Finsler structure, and this Finsler structure is called Randers matrix. Randers was actually a physicist, and he used this metric too much in physics, in fact. So these are, well-known indicatrices in Euclidean plane, in every tangent space, the same unit sphere. This you can think of the indicatrices in Riemannian plane. The center is at the center of ellipse, and you can think of this as the indicatrices in Finsler plane. So in every tangent space, at every point you have a tangent space, and this is my indicatrix at this point. So just it's constructed in such a way that it's moved by a translation. So it's a Minkowski, you may call it a locally Minkowski space. In every tangent space you have the same indicatrix. Okay, so now you have a Finsler structure. In every tangent space you have a norm. So what is its advantage? So the advantage is that you can measure the length of a smooth piecewise smooth curve defined on this interval. So suppose gamma is a piecewise smooth curve, you can measure the length. And then you can talk about the distance between 2 points. So the infimum of arc length running 2 point, so this is the distance. But interestingly, the length of the reverse curve may not be equal to the length of curve. The length of, if you define this gamma inverse as gamma A plus B minus T, this is the reverse curve. So its length may not be equal to, because when you go, just because of the condition that norm of minus B is not equal to norm of B. So if your Finsler metric is not reversible, then the length of gamma may not be equal to the length of gamma inverse, and therefore in general it's not gives symmetric metric. So distance between P and Q may not be equal to distance between Q and P. Now, why we put such a strong condition? So this is one of the advantages of assuming this is strong convexity condition, that it gives actually an inner product in every tangent space in a fixed direction. So the Hessian of f square induces a direction dependent inner product in each tangent space of the manifold, and that it's called a fundamental tensor in Finsler geometry. So at every point, so in this tangent space, if you have a vector, so with respect to this vector, you have inner product. So if you take another vector, you have in the same tangent space, you have another inner product. So our inner product is actually direction dependent. So direction dependent, I'm not saying vector dependent, it's actually direction dependent because of this reason. Because when you just scale via this positive constant, this the components of the inner products are same, and this is because of the homogeneity condition of the norm. And the norm and this fundamental tensor, this is interesting relation, and it turns out to be a consequence of the homogeneity condition. That it's exactly look like when you have a Riemannian metric. So the norm of a vector v in a Riemannian metric, is equal to this Gij, and suppose this v is a vector in the tangent space Xm, and this Vi Vj. Now, Karta introduced a tensor. This is very interesting tensor. The component of this is actually a 0-3 tensor, and it was defined by just the vertical derivative. There are two directions, horizontal direction and vertical direction. So the vertical derivative of this fundamental tensor, and it turns out that a Finsler metric is Riemannian if and only if the all Karta tensor vanishes identically. So this is it's a differentiation between how you choose this Riemannian metric among Finsler metrics. So if its Karta tensor vanishes identically, it's actually a Riemannian metric. Now, just like Riemannian setup, a geodesic of a Finsler manifold is a critical curve of the energy functional. It turns out that geodesic of a Finsler manifold are given by the following system of differential. This is exactly look like your geodesic equation of Riemannian setup. The only thing is that here the component of the Christoffel symbols, they are functions of x and also direction, because your fundamental tensor, your metric tensor was, it depends on point and also on the direction, and that is why this Christoffel symbol depends on x and this direction also. So this is actually a second order non-linear differential equation, but because we are in a smooth setup, it always gives, maybe for short time, but it always gives for given point and given direction unique geodesic. So for a given vector, we denote by this gamma ut, the geodesic with initial value, this gamma u0 is p, and its initial velocity is u. So now at each point p, this exponential map is defined from a tangent space to the manifold. It's exactly, it's defined like in the Riemannian setup, because you have geodesic. So now the interesting consequence about this exponential map is that it's a C1 at the origin. It's not like Riemannian setup, which is C infinity. It's only C1 at origin, and away from the origin, it is C infinity. And here is the result of Akbarzadeh to prove that this exponential map is C2 at the origin if and only if it is C infinity at the origin. And in that case, this Finsler manifold has a special name, what is called a Burwood manifold. Yeah, but I have not defined, so I will not say that. Now, just like a Riemannian setup, there is a fundamental theorem that there exists unique affine connection on a Finsler manifold, which is torsion-free and almost metrical, and such a connection is called Chern connection. In fact, there are a lot of connections well known in Finsler geometry, but there is no connection which is torsion-free and metrical like Riemannian setup. So either you have to, in fact, there is a theorem that if it's torsion-free and metrical, this Finsler manifold forced to be a Riemannian manifold. So either you have to weaken the condition of torsion-freeness or of the metrical nature. So, but there is a unique connection which is torsion-free and almost metrical. And the component of the, this is called Chern connection. So it's not exactly the Christoffel symbol, but it's a combination of this Christoffel symbol with these Karta tensor and non-linear connection, where it's a highly tensorial notations are involved now. So this non-linear connection given by this, where Gi is again coming from the Christoffel symbol. But it's interesting that when Karta tensor 0, that is your Riemannian, your Finsler metric is Riemannian, this Chern connection is nothing but the Levi-Civita connection of the Riemannian geometry. So in that sense, it's actually generalization of the Riemannian Levi-Civita connection. Now, this oscillating Riemannian metric is a very interesting notion. So I will say why. So let MF be a smooth manifold with a strongly convex Finsler metric, and X naught J naught is an element here, a non-zero part of the tangent bundle. Now, a vector field V defined in some neighborhood O of the point V0 is X0 is said to be a geodesic extension of J0 if at the point is J0 and if the integral curves of V are geodesics of the Finsler metric F. In particular, I mean, nowhere 0 on the neighborhood. Then this oscillating Riemannian metric. So in fact, you have a vector field on, you take an open set and you have a vector field, non-vanishing vector field. So whatever point you choose, you have a direction. And when you have a direction, you have a unique inner product. So in fact, on that open set, you have a unique inner product on every tangent space, and that gives a Riemannian metric, and that is called actually the oscillating Riemannian metric. Now, this oscillating Riemannian metric is quite important because this let MF be a smooth manifold with a strongly convex Finsler metric and Xi be a point in this non-zero part of the tangent bundle. Then this Riemann curvature is well defined independently of the choice of geodesic. So whatever geodesic extension you take, I mean, it's independent, and that is why it's important. So these are the component of Riemann curvature, and I mean, then a lot of things you can do. For example, you can talk about the Ricci curvature, and also you can define a notion of flag curvature, which is the analog of sectional curvature in Riemannian geometry. So the flag curvature here, you know, in sectional curvature, on any tangent space, if you have a two plane, you can get sectional curvature. So here on a two plane, you have to fix the flag pole. So a flag pole, a two plane, and then, I mean, that is why it is called a flag. It's given by the same formula as, you know, in the Riemannian geometry. And so it's actually depend on the point, depends on a vector, and it depends on a two plane. Yeah, so the flag curvature, in fact, is independent of the vector V, and that is why it is well defined. But in general, it depends on the flag pole. Now, a Finsler metric is said to be a constant flag curvature if this Fxjp is constant for every point, for every vector, and for every plane. It's said to be scalar flag curvature if it is, it only depends on x and j. It should not depend on the plane. So you take a point, you take a vector, for any two plane containing the vector should be same. It is well known that a Riemannian metric of constant sectional curvature, it is completely classified. Locally, it's either Euclidean, spherical, or hyperbolic. But the classification of Finsler metric of constant flag curvature or even scalar flag curvature is not known. So in particular, for Rander's case, it is done. It's not long back, maybe in previous decade it was done. So it is completely classified, only the Rander's case, and now people are doing, I mean, for various Finsler metric of constant flag curvature or scalar flag curvature. Now, what are the major theorems for this constant flag curvature is by Akbar-Jade. He proved that a compact, I think it is 1988, not 98, sorry. A compact Finsler manifold of constant flag curvature, K is locally Minkowskian if K is equal to 0, and is Riemannian if K is negative. So in fact, I mean, so there is no hope for, I mean, people of Teichmüller theory here, because, you know, for compact manifold, if you have a constant negative, for example, in Riemannian setup, you develop a lot of theory, but if you want to put a constant negative curvature on a compact manifold, it has to be Riemannian. And for constant positive flag curvature, in 97, Robert Bryant constructed a family of non-reversible Finsler metric on 2 sphere, I mean a huge family. So after this flag curvature, there is a notion of volume form in Finsler geometry, because there is no standard volume form. It is well known that there is no canonical, for example, in Riemannian geometry, there is a well-known canonical volume form, but in Finsler geometry, there is no canonical volume form, and there are several volume forms. So the reason is that because this metric tensor depends not only the point, but you want a volume form which only depends on the point, not on the direction. So there are several well-known volume forms. So I only define this Buchmann-Hausdorff. So this on tangent space, these coefficients, they are actually the ratio of the volume of Euclidean ball and your Minkowski ball. So at every point, you just take the ratio of Euclidean ball and Minkowski ball, and then you have a notion of volume form. And in fact, when your metric is Riemannian, this is exactly the Riemannian volume form. In fact, all the volume forms what was developed instead of a Riemannian geometry, it's actually the Riemannian volume form. And I mean, this is the simple computation for Randers metric alpha plus beta. The volume form is given by this. So it's always, because this norm of beta is always less than 1, it's always less than the volume of the Riemannian setup. I mean, the volume of the Buchmann volume form of Randers metric is always less than equal to this. And here is the notion of a distortion. And this distortion is used to define, it's actually a non-Riemannian quantity here. Because when you have a Riemannian metric, this volume form is exactly equal to this square root of determinant of Gij, and in that case, this torsion becomes 0. So it shows actually that how much it's differ from the Riemannian setup. And then Jet Shen, he defined this notion, and that is why it's called S curvature. For a given geodesic, the S curvature of a Finsler metric is defined like this. It's the rate of change of distortion along some geodesic. And it can be computed, this is a simple formula through this volume form. Okay, so I have introduced a lot of things. Maybe it's most of the things are disjoint from several. So if so far any question or comment? So this is this. Yeah. So here I am differentiating this distortion along the geodesic. So distortion was defined in terms of here. Yeah. So how much it's differ from the Riemannian setup, and then I am differentiating along a geodesic. So a geodesic is given, and then I am looking at how much is distort along the geodesic. Okay, so so now after this I will discuss standard, very well-known metric example of Finsler metric, what is called Funk metric. Let us consider a convex set omega in Rn. So in fact, if I am correct, this was the notion of Professor Athanase, what is called tautological Funk-Finsler structure. Tautological Funk-Finsler structure for a convex set is the Finsler structure for which the unit ball at a point x is the set omega itself with x as its center and is given by. So what it says, so you take a convex set, in fact, it may not be a circle here, I am defining it may be any convex set. It may be any convex set in Rn. It may be any convex set in Rn. And at each point, you have a tangent space. And in every tangent space, you think of this ball as a unit ball. At this point, you think of this ball itself as unit ball centered at this point. At this point, you identify this tangent space and you consider this ball there and this ball itself as a unit ball in that tangent space. So such a structure is called this tautological Funk-Finsler structure. So, I mean, this I want to measure the length of this vector chi at the point x. So in the tangent space, this Tx omega, you can think of, you just draw this ray which intersect this boundary of this convex set at the point A. So this Finsler structure is actually that how much times, this you just increase this chi to hit this boundary, right? So in fact, it's the infimum of this scalar t such that x plus chi over t hits the boundary. So by a simple computation, because this x plus chi over this norm of this chi, it belongs to this boundary of this, it's omega in fact, sorry, it's omega. So yeah, so here I am actually considering, I am computing now. So I am considering this omega to be unit ball, my unit ball in Rn. In fact, I have written unit disk, but it's actually unit ball in Rn. And it turns out by a simple computation that this f is written in this form. So this Finsler structure is given via this expression. And here you see this is your well-known Klein metric on the unit disk. And this is a one form on the unit disk. So therefore, this Funk metric on unit ball is actually a Render's metric, where there is the Riemannian part is the well-known Klein metric, and this is a closed one form. It's a closed one form. So the Funk-Finsler structure of the unit ball is given via this previous expression. And now interestingly, because this beta is a closed one form, so there is a result that if the one form is closed, the geodesic of alpha are geodesics of your Render's matrix. So actually, because the geodesics of the Klein metric are line segments here, so the geodesics of this Funk-Finsler structure are also line segment. And the Funk distance induced by this Finsler structure is given by this formula. So if you have a convex set here, in this case it's unit ball, and take a point this x1, x2. Suppose it hits the boundary at the point A. So you compute this distance between x1a, x2a, and take the log. This is the distance between x1 and x2. So someone was asking that about the non-symmetric distance. So you see the distance between x1 to x2 is not equal to distance from x2 to x1 here, because when you compute distance from x2 to x1, you have to take this ray, and if hits the boundary here, you have to compute the ratio of x2 minus b to x1 minus b, and then you take the log and compute. And interestingly, in this case, if you suppose you want to measure the distance from origin to boundary, it turns out to be infinite. So it's forward complete. So one way it's complete. But when you go back, when you want to compute the distance between any point close to boundary to origin, it turns out to be finite. It's log 2 actually. And we define this flag curvature. So for here, it turns out that this Funk-Finsler structure is of constant flag curvature minus 1 over 4. The Funk-Finsler structure has this constant flag curvature. So it's almost very close to your hyperbolic metric. But just the difference is that it's non-symmetric here. So the Funk-Finsler metric is forward complete, but it's not backward complete. Now here is another Finsler structure, which is called Hilbert-Finsler structure, which is a symmetrization of this tautological Funk-Finsler structure. So you just compute the distance, I mean, for any vector xi, you just compute the Finsler Funk structure of xi and then Funk structure of minus xi, and you symmetrize this. Now, for this Finsler metric, you see this fhx minus xi is equal to, so it's a reversible Finsler metric. This Hilbert Finsler structure is actually reversible Finsler structure. And for unit disk, it turns out that this Hilbert metric is nothing but the Klein metric, exactly the Klein metric. And the geodesic of this Hilbert Finsler structure for this open unit disk are line segments in the open unit disk. And the distance formula is exactly given by this expression. And because it's a Klein metric, I mean, it's well known that it has constant flag curvature -1. Moreover, this Hilbert Finsler metric is both forward as well as backward complete. So now, as you see this in this unit disk case, it turns out to be a Riemannian metric, it's a Klein metric. So here is a characterization that the Hilbert metric in a bounded domain omega with smooth strongly convex boundary is Riemannian if and only if omega is an ellipsoid. And the second result for this, let F be strongly convex Finsler metric on a bounded convex domain omega, then F is Hilbert metric of that domain if and only if. So this projectively flat means its geodesics are line segments. Geodesics are line segment. If its geodesics are line segments, it's called a projectively flat. It's a complete and has constant flag curvature -1. Now we'll talk more about this Funk metric. So as you know, in for this hyperbolic metric, you know that it can also be viewed as, so you take this Lorentzian metric and its pullback on the hyperboloid of upper sheet is actually turns out to be Riemannian metric. Sometimes, I mean, it depends on which immersion you are considering. It turns out to be Poincare metric or Klein metric. So here also we have considered a deformation of this Lorentzian metric in R3, and more generally you can also talk about in Rn+1, and its pullback on upper half portion of the hyperboloid is actually turns out to be the Funk metric. Yeah, so this is I mean, this Lorentzian metric in R3, and we considered this deformation via along this z-axis, and then its pullback on this hyperboloid of upper sheet, it turns out to be Funk metric on the unit disk. Now, Papadopoulos and Yamada have defined this variational Funk distance in open bounded convex subset omega equipped with the Euclidean metric as this. So what they consider, so for any convex set, so suppose this is a convex set, and you take this as supporting hyperplanes. So this pi is supporting hyperplane, and suppose you have to find the distance between this x1 and x2. So they define the distance like, take the perpendicular distance from this point, say x1 to this hyperplane, supporting hyperplane, and x2 to this hyperplane. Maybe you can think of this as m and n. And take the infimum of this ratio for all supporting hyperplanes of this convex body. And it turns out that if this convex domain is strictly convex, the supremum is achieved when this point of intersection of this ray passing through x1, x2 and the supporting hyperplane is at this point of contact. And therefore, for a strictly convex domain, this new definition of this variational Funke distance is exactly what we defined the Funke distance in earlier case. Now, considering this viewpoint to the variational approach of this Funke distance, in constant curvature spaces, you know, this sign formula in Euclidean geometry is given by this, in spherical geometry is weighted by this sign, and in hyperbolic geometry it's weighted by this Finch. And also you have the sign formula, you also see the similar thing. And moreover, when you consider the similarity, so for similarity in Euclidean triangles, you know, you just divide this AB over AB dash, BC over B dash, C dash, and so on. But in spherical geometry, you have to weight it by this sinh and sine. So considering this viewpoint and this variational approach of this Funke metric, they define the distance between 2 points. So here I am considering a convex set in hyperbolic space. So the distance between 2 points x and y. So suppose now I am considering this convex set in my hyperbolic space, and now this is my supporting hyper surface, and you can define it similarly. So this x1 to say this is my pi, x2 to pi, and again it turns out that if your domain is strictly convex, the distance between x1, x2 is log of sinh of distance between x1 to a and sinh of distance between x2 to a. Now I am considering this for a special case, I am considering this Klein unit disk, and within this Klein unit disk we computed this Finsler structure for this this Funke metric, and it turns out that it's again a Randers metric. Is given by this Riemannian part, which is again the Klein metric, and this is a closed one form. So again it's projectively flat Finsler metric, it's geodesics within the disk or line segments. And also on a sphere, you consider the same idea, you take a convex set. The only condition is that here the diameter of omega should be less than pi by 2. And then you take supporting hyperplanes and the distance from x to supporting hyperplane, y to supporting hyperplane, and its ratio, you define this as the Funke metric on the convex set of a sphere. And again it turns out that if it is a convex, I mean strictly convex, so here is your sphere, and suppose this is my convex set, so the distance between x1 to x2, suppose this geodesic intersect at the point A, so you compute this spherical distance from x1 to a and x2 to a, and take its sign and then take the ratio log, and that is the Funke structure on this sphere. And in that case, this Finsler structure is given by this formula, but explicitly in coordinates we have computed that it's again a Randers metric with this alpha as a Riemannian metric and beta is a closed one form. And in fact, we combine all the three cases for spherical case, hyperbolic case, and Euclidean case, and in a single formula, it can be written in this form, that the Funke metric centered at origin is given by a Randers metric where alpha is this and beta is this. I mean, this is long computation. We computed the Riemann curvature, Ricci curvature, and Flack curvature for this Funke metric in constant curvature spaces. And also we computed this S curvature for this Finsler metric in constant curvature spaces. And it turns out this interesting fact that the flag curvature of Finsler metric in hyperbolic space is bounded above by -1/4. In spherical case, it's bounded below by -1/4, and in Euclidean case is exactly -1/4. And in similar computation for S curvature, it turns out for Euclidean case, it's already known to be 3/2, but in this case, for this constant curvature spaces, it's bounded above by 3/2, and in spherical case, it's bounded below by a 3/2. So I mean, it's obvious because I mean this, it's a constant negative curvature. For the hyperbolic case, it has constant negative curvature. It's less than -1/4. So it's actually a Cartan-Hadamard manifold. And further, for this hyperbolic case, this S curvature is less than 1/4. But it's already known that if flag curvature is negative and S curvature is negative, then there are several inequalities. I mean, people are using this functional inequalities. It holds if flag curvature is negative and S curvature is negative. In our case, the flag curvature is negative, but S curvature is less than 1/4. So I hope that in this some subset of this, I mean, space, and we have to find what subset we have to take, these inequality will be satisfied, definitely satisfied. Or another way, some of the inequality can be extended to our setup, where S curvature is less than 1/4 and flag curvature is negative. These are my references. So any questions? Yes. No, non-curvature, I mean, you were talking about the non-curvature in what sense? Flag curvature. Non-curvature means flag curvature, or in sense of Bushman? Yes, yes, yeah. Yeah. Yeah, yeah, yeah. Yeah. So you can only define this flag curvature if everything is smooth setup. Yeah. So in a smooth setup, I mean, it's equivalent. But if it's not smooth, then I mean, there is no meaning to define this flag curvature there. You can define only flag curvature if your metric is strongly convex. Right? Yeah, yeah, yeah. Geodesics, all the geodesics here are straight lines because they are projectively flat. No, no, even if you symmetrize, so what you will get a Riemannian metric. In our case, you are saying, no? Yeah, so it's a Riemannian metric that is projectively flat. So in this chart, it's actually straight lines, line segments. Or in particular, if you look on the manifold, they are part of the great circles. Or in hyperbolic space, I mean, as you know, they are part of the circles intersect boundary circle orthogonally. No, he was talking about the non-positive curvature in Bushman sense. Yeah. Yeah. I think if this flag curvature is non-positive, in that case, I am not sure, but I mean, I hope that this it is also true in the sense of Bushman, because I mean the people are studying this non-positive curvature in this Bushman sense. No. It's only defined once you know this Riemann curvature. And for Riemann curvature, you need all these setup, this tensor, fundamental tensor, and yeah. No. These no. In general, at least not. But in some special case, it may be. So, for example, there is a paper by Athanase and Ohshika. So there, I mean, they discuss about the Teichmüller metric and Thurston metric on their analogs on the torus. And there they computed this Thurston metric and this Teichmüller metric. And it turns out this Teichmüller metric is exactly the hyperbolic metric in upper half plane. It's an analog of hyperbolic metric. And this Thurston metric is a kind of Renders metric, but it's not positive definite Renders metric. In fact, they defined a more general metric which lie in between these two. So they define a parameter, for parameter value 0, it's become a Thurston metric, and for parameter 1, it's become Teichmüller metric.